Okay, so we looked at surface tension and viscosity. Now we want to talk about what happens as we are changing from one physical state to another. And we're talking about solid, liquid, and vapor physical states, right? We're not talking about driving across state lines to Ohio or something. So these are the definitions. Evaporation, condensation are the two opposites, going from liquid to gas or gas to liquid. Sublimation and deposition are the two in opposite directions between a solid and a vapor. You all know of sublimation from dry ice. That's what most people see as a kid. You have it at Halloween parties. Solid carbon dioxide just sublimes. And also you might have had some experience with the iodine. The iodine we used in the zinc iodide lab, that also sublimes. But did you notice that you could really smell it when you opened the container? You could smell that halogen iodine smell, kind of like betadine from the hospital that you might be familiar with. That's because the iodine actually sublimes. So it's going into the vapor so you get a really good whiff of it. And deposition is going the opposite way. And then melting in chemistry, melting is called fusion, not nuclear fission and fusion. And that's going from a solid to a liquid, and freezing is liquid to solid. And when we think about this, we can look at the relationship between kinetic energy and the energy it requires to make these phase changes. We know that kinetic energy is directly proportional to the Kelvin temperature, and we have a higher average kinetic energy at a higher temperature. So liquids are collections of high kinetic energy or fast-moving molecules and low kinetic energy molecules also. So if we look at this drawing, what we're plotting on the y-axis is kind of the fraction of molecules with a given kinetic energy, and here we're plotting kinetic energy. Now, this is not kinetic energy increasing. I kind of think of this curve more like little slices of a bar graph. And so it kind of looks like this. So you could think of it as that we have this many molecules with a low kinetic energy, and then as we go up higher, we have more molecules. Then there are fewer molecules with these higher kinetic energies out here. And somewhere in there we have the average. But let's say that this is the minimum kinetic energy required to make a phase transition. So only these molecules can actually make the phase transition, because these other guys aren't moving fast enough to be able to break away and break those intermolecular forces. So if you think about this, when you have a liquid that has weak intermolecular forces, the molecules are just kind of sitting next to each other and they can break away. If you have high intermolecular forces, the molecules are hanging on to each other. You have to break away from them to be able to escape. So we need a minimum kinetic energy to have enough energy to make that transition. Now, we have to have a fast-moving molecule, and it has to be also at the surface in order to break away. So if we think about this, if we have our liquid, if a molecule's down here, no matter how fast it's moving, it cannot evaporate because it has to be up here in order to be able to evaporate and make that phase transition. So when we're talking about evaporation, as these molecules, fast-moving molecules, get to the surface, the kinetic energy of the whole system drops, and as the kinetic energy of the system drops, the temperature drops, because kinetic energy is proportional to the temperature is proportional to the average kinetic energy. So when the kinetic energy goes down, because all the fast-moving molecules are leaving, then the temperature goes down. Okay, and think about it. If you're confused about this kinetic energy, if I said anybody in this room that's taller than 5'8", please leave the room, what's going to happen to the average height of those left in the room? It goes down, right? I mean, we didn't shrink. It's just that only the short ones are left. And that's what's happening. Only the slow-moving molecules are left because the other guys left. And this temperature goes down. Now, when the temperature goes down, that's because evaporation is a cooling process. but you knew this. This is why we sweat, right? We sweat because it's our body's cooling mechanism. So that when we get hot, we generate that perspiration, it sits on our skin, and then it goes and evaporates into the air. As it evaporates, it cools us down. Now, sometimes in Michigan, in the summertime, you're sitting there, it's 98 degrees here in July, and it's 99% humidity. What happens when you sweat? Do you cool off? No, you just sit there and drip because the humidity in the air is so high that you cannot evaporate that sweat on your skin, so it doesn't work to cool you off. Okay, it's different than if you go to Arizona or someplace that's really dry. The humidity in Arizona is so low that as soon as you start to sweat, it evaporates, and you might not even be aware that you're sweating, and that's cooling you off. Although in Arizona, when it's 120 Fahrenheit, even that sweating doesn't seem to cool you off. It's still hot there, right? I mean, you go there and they're like, oh, it's a dry heat. Yeah, it's a dry heat. If I want to get in the oven, I'd feel the same thing, but I don't do that. Okay, so that lack of humidity. And I noticed when I was there and we went swimming, even though it was 115 degrees and we're out in the middle of the sun where the pool was, when I got out of the pool, I was really cold. I mean, I was uncomfortably cold that I didn't just sit there. I went and got a towel because that evaporation is taking place so quickly that my body temperature was cooling right down, surface temperature. And that doesn't happen. When I get out of a pool in the summer in Michigan, I can just hang out and be wet, right, but not be uncomfortable. Okay, so evaporation rate depends on several different factors. It depends on surface area, temperature, and intermolecular attractions. At a higher temperature, you get more evaporation because molecules are moving faster. When you have a higher surface area, there's more surface, so more molecules are at the surface, so it's easier to evaporate. And when you have weaker intermolecular attractions, it's easier to evaporate and you get more evaporation. And stronger intermolecular attractions, you get less. So when we look at this summary chart, as intermolecular forces increase, evaporation rate goes the opposite way. You get more evaporation with low intermolecular forces. So if we look at this, think about these things. Which would evaporate faster? Water that's in a pie plate or water that's in a bud vase? Pie plate. Why? Has a higher surface area, right? Everybody knows what a bud vase is, right? It's a skinny little flower vase that just holds one stem of flower. And I think everybody knows what a pie plate is, but I think we're going to see some later. And water or hexane in the same kind of container, which would evaporate faster? Hexane. Why? Yep, has lower intermolecular forces. Okay, and then when we talk about the condensation rate, that depends on how quickly the molecules are colliding with the surface of the liquid, because when they have that collision, it's non-elastic and they have to come back. And when you have evaporation taking place, you'll also have condensation. If we put something in a closed container, eventually we will get to equilibrium, where we have material evaporating and material condensing at the same rate. Because it's closed off, we get a certain amount of vapor up there and then it will start to condense. So we talk about dynamic equilibrium where we have two things happening at the same rate. The reaction is going forwards and backwards. And we can get the same equilibrium with melting, freezing, or sublimation deposition. Okay, so that's kind of a quick overview of these phase changes.